Were you able to pause, or did you just start a new one? Yeah. Okay, are we live, Lillian? Do you hear me yet? You don't have to watch the live stream, obviously. Oh, actually, you do, because, well, you'll be able to answer most of the questions. It's helpful to have the live stream just for the chat, because a lot of questions, in general, people start asking a lot of questions, and you guys can respond to the chat as well, and raise your hand here and ask a good question. Even if you know the answer, if a couple people are asking the same thing, just raise your hand. 8 o'clock. Welcome, day 2, everyone. How many have joined the live stream? Can we tell? 32. we start at 8 sharp. Those of you who haven't come to Berkeley yet, there's this thing called Berkeley time. Berkeley classes say 8 a.m., but we actually start them all at 10 past the hour, which is just the silliest thing. Just say 8:10. If it starts at 8:10, say 8:10. So what they do is they just build the walk time between classes into the hour-long block that the classes are scheduled. So the first 10 minutes are walk time. But it confuses everyone, and everything at Cal. You'll have a meeting and you'll schedule for 8 o'clock, and people will not show up till 8:10. It's just silly. Anyway, we're gonna pick up where we left off last time, and I wanted to discuss this whole idea of relative masses again, because some people were a little confused by it, and it's not a confusing thing. What might confuse you, especially if you had like AP chemistry or something, those first chem quizzes that were, rock, paper, scissors and relative mass. If you've had chemistry already and you're thinking maybe in the back of your mind about the mole concept or something, it kind of you want to do this procedure that you're good at doing, and it kind of stops you from just thinking about what's happening. It all is just relative masses. So that's why I'm going through this to say that you do the same things with atoms and molecules that you do at the hardware store. It's no different. If you go to the hardware store, you could explain the mole concept to them; they would get it, because it's just relative masses. So what does this mean? These relative masses are telling us the mass of some amount of these things, but it's not any specific amount. It's just telling them relative to each other. So a staple weighs 1/12 of a scissor. We don't know how much a scissor weighs, but if it's a scissor, we could just weigh one of them. So if a scissor weighed if a scissor weighed a gram, then a staple would weigh 1/12 of a gram, one of them. And the units don't matter. If a scissor weighed a pound, then a staple would weigh 1/12 of a pound or a kilogram. So the units don't matter with the relative mass. It's just what's relative to each other. But it works if you multiply. If you have 10 scissors, then that's 10 pounds. If you want 10 staples to do that, that's 10/12 of a pound, 1.2 pounds, 1.2 kilograms, 1.2 grams. It doesn't matter what unit they are, as long as the units match and you use the relative masses, then you can determine how many things you need to mix with each other. And we did that problem last time where we took nuts, bolts, and washers, and without knowing how many nuts, bolts, and washers there actually were in our 2 tons of bolts, we could make sure we had a bolt, 4 washers, and 3 nuts when we left the hardware store, just by saying how much mass of each one we had. And when we said we want 1,200 pounds of bolts, we also know, I know about how much total mass I'm going to leave the hardware store with. I know how big a truck to bring, because I can calculate the mass of the other things. And that's a chemistry question. We'll tell you, we'll give you a chemical reaction and say, here's the chemical reaction. You start with X grams of this. How many grams of that will you end up with? And all it is just adding up the relative masses. So it's a relatively, it's a very simple concept. What we can, and like I said, in this case, you could measure the mass of one pair of scissors, but it's hard to measure the mass of one atom. So you don't worry about it. Don't worry about the mass of an atom. Just worry about the relative masses of everything. And don't worry about the exact number, because if the relative masses are correct, you have the right numbers of particles. That's kind of the key thing. You're getting the right number of particles just by the relative masses. And that's what you want to do. And that's what's hard in, not hard, but that's what's chemistry you can't do. You can't count out a dozen carbon atoms and a dozen hydrogen molecules to react together. So you just use their relative masses to make sure you have the same number of particles in your reactions. And of course, we multiplied through by the common, the mass of the lightest element in our table, and got these up to values greater than 1. That's just a matter of convenience. Makes the table a little more friendly and easy to read. And so we understand that this is a straightforward way to use to do the same thing we do at the hardware store with atoms and molecules in a chemical reaction, because we can tabulate relative masses of atoms and molecules. We put the relative masses of all the atoms on the periodic table. And here's a table, it's a combination of atoms and molecules. So hydrogen, relative mass 1, hydrogen, relative mass 2, because it's 2 hydrogen atoms. And here's carbon, relative mass 12, oxygen, relative mass 16. Here's an isotope of oxygen. Here's oxygen with 2 extra neutrons in the nucleus. So remember, we said last time the mass number isn't unique. The mass number does not tell you what the particle is. It's only the number of, if it's an atom, it's only the number of protons in the nucleus. So this oxygen still has 8 protons in its nucleus. It just has an extra 2 neutrons. And those don't in general affect the properties very much. They affect the mass, but in 99% of the things we do, the mass of the particle doesn't matter. The nucleus doesn't matter. It matters, we'll talk about it just in a minute, of how we get these relative masses. But if you just had something of a mass 18, you wouldn't know if it were a water particle, which also has mass 18, an oxygen and 2 hydrogens, or an O18 nucleus. So the mass is not unique, but the relative masses are very helpful. And you can see we have 3 flavors of carbon, carbon 12, carbon 13, and carbon 14. I have this one in orange because it's not stable. This is a radioactive nucleus, so it decays to carbon 13. These nuclei are very important for our study of just a myriad of things. Certainly carbon dating. This decays at a relatively known rate. And you renew the carbon 14 in your body. There's about 1 in 1,000-ish, I think, carbon 14s. There's 1 in 100 carbon 13s in a sample of carbon. These all occur in natural piece of carbon. So if you have a piece of carbon, if it's new organic carbon, then you know the ratios of these. This is about 100 to 1, and this is about, I think, boy, I'm bummed that I don't know that. I should have looked up something like 10,000 to 1 in naturally. It would vary depending on where the natural source is. And that's kind of the point. If you have some carbon and you eat something that has natural carbon, like leaves or protein or something that's been living on the earth, it has some natural carbon in it, but it can't get any more natural carbon while it's in your body. So if you die and you stop taking in natural carbon, or anything dies and starts taking natural carbon, the carbon 14 decays away at a known rate. So you could take a sample of your body, measure the carbon-14, and see how long ago you died. If you're a plant, animal, dinosaur, whatever you are. So that fact that there's a mixture of those nuclei is has some value, those relative masses that we can measure. So we can also use them to do our chemical calculations. We've already seen that. Just if you have, say, 18 grams of water, that has the same number of particles as 32 grams of oxygen molecules. Super handy. So if you want to react uh, water and oxygen, it's hard to get those two to react, but if you wanted to do them 1-to-1, you'd take 18 grams of water and 32 grams of oxygen. If you wanted to react them 1-to-2 or something like that, just multiply the relative mass to get the right number of particles in your sample. Here's carbon dioxide, 44 is its relative mass. Now, so these relative masses are going to help us do all kinds of calculations. And I think we're just going to do one right now as a chem quiz. So here is a chem quiz. What mass of sulfur, so solid natural elemental sulfur, is required to react completely with a gram of oxygen molecules? And I put the relative masses here again so you can see them, the atoms of these particles. So take a minute, talk among yourselves, and I will start a chem quiz. When I start it, that captures the screen, and you guys have this now in your iClicker app. So I can go to this screen, which has all the recent information that you had that might help you. So if you look at the live stream, you can look at this, and that might be relevant information that you need. So think about that for a minute, talk among your friends. I'll pop into a Zoom room and we'll reconvene here in a couple minutes. Hey guys, I just heard in my Zoom room that some people are having trouble seeing the question. I'll go back to it here. Is anybody else running the iClicker app? Is anybody else? Can you see it like on your phone? Yeah, you can see the question. So if you have iClicker running, it should capture the screen. Okay, guys, I had a great discussion with the people in my Zoom breakout room. I hope you guys did too. Um, didn't hear you chatting. Were you in a breakout room, Lillian? With the chat? Oh, goodness. So the GSIs are joining breakout rooms as well. So you'll see them occasionally and you'll see me occasionally in your breakout room. So let's talk about this. Let's see what the result of the vote is first. And I know this is a little hard for you guys to see, but we have A, B, and C here. And A is by far the most popular, 84%. And I will tell you, I agree with the A's. And why is that? Well, this is the chemical reaction, and we know the relative masses. The relative masses are 32, and for oxygen atoms, 16. So oxygen molecules would have relative mass 32 because there's 2 oxygen atoms there. So sulfur and oxygen molecules have the same relative mass. That means 32 grams or 32 kilograms or 32 pounds of sulfur and oxygen molecules have the same number of particles. That's how simple this is. The people in my Zoom, they wanted to convert to moles. Which I haven't even talked about yet, and I won't give you a chem quiz where you have to do something I haven't talked about yet. Now, it's fine to convert it to moles, and if you know how to do that, that's fine. Maybe you've had AP chemistry. Absolutely not necessary, and it's an extra step. All you need to know is 32 grams of sulfur have the same number of particles as 32 grams of oxygen molecules. So that means 5 grams of sulfur have the same number of particles as 5 grams of oxygen molecules, or 1 gram of oxygen molecules has the same number of particles as 1 gram of sulfur particles. And since they react 1 to 1 in this equation, 1 gram of sulfur will react completely with 1 gram of oxygen. And it'll give you a mass of sulfur, and you can calculate the relative mass there. That's 32 plus 32, or 64. So that's twice this. So it's going to give you half a gram of, half. It'll give you 2 grams of sulfur and sulfur dioxide. And you didn't even have to know that, because if you started out with a gram of this and a gram of this, mass is conserved. So every gram of this and every gram of that react to form this, and you'd have 2 grams of sulfur dioxide at the end. So these relative masses are the same. So this is the answer here is 1. You guys all got that. Interesting thing, what if you didn't have? What if you took your 1 gram of, and notice I just put mass here because that could be any unit. So what if your 1 gram of oxygen reacted with only half a gram of sulfur? Well, in that case, the oxygen would start reacting with half a gram of sulfur. You'd use up that entire half a gram of sulfur. You only have half the number of particles you'd need. You'd use them all. But you'd still have left half a gram of oxygen. You'd have that, those half the particles left over. So not having enough can limit the reaction, how far it goes. So if you don't have the right number of particles, reaction will still go, but the smallest number of particles will limit how the reaction goes. It's not the smallest mass. You have to make sure it's the smallest number of particles. So you have to look at the relative masses. So half a gram would proceed. And if that happened, you'd only make 1.5 grams of your sulfur dioxide, because half a gram would, a gram, half a gram of your oxygen would react fully with that half a gram of sulfur that we said we had. And that makes a gram of this and leaves behind the half gram of oxygen. So you can still conserve your mass across that and make sure you have mass left over on this side now. You have half a gram of oxygen left over, and you have your gram of sulfur dioxide. Half a gram reacted gives you a gram over there and gives you your half gram of oxygen remaining on this side. So you can always conserve mass. You can always use the number of particles to calculate through this. Okay, how do we get those relative masses? So there's a device called a mass spectrometer. We don't really have to know exactly how this works. It's interesting. So I will tell you, you take a sample, particles, you atomize them. So it's all atoms, and then you ionize them. That means remove some electrons. And when you remove electrons from those particles, they have a charge, because naturally the positive charges in the nucleus are balanced with the negative charges of the electron cloud. If you make that unbalanced by removing some electrons, you have a net positive charge left on your particles. So they go through this, then you accelerate them towards a negative charge. So positive charges are attracted to negative charges. So they get positively charged here, they're attracted and start zooming towards the negative charge. They go zoom through there and then through a magnetic field. And it's an asymmetric magnetic field. You don't have to know all this physics, but when a charged particle, and you will learn it, when a charged particle passes through a magnetic field, there's a force on it. In this case, it's a skewed magnetic field, so it bends the path up here, but it bends it depending on the mass. So light particles are deflected a lot, and the heavier particles are not deflected as much. So you would get a signal, whatever your detector is here, for that light particle. And if you went with a heavier particle, it wouldn't be deflected as much, and you'd get a signal at a different place on your detector, different energy, depending on how you're doing the experiment. And you could plot that out. And it's exquisitely dependent on mass. So you can plot the masses of your particles from that detector. And we generally just write it as a mass axis. So if we do a mass spec experiment and we got a peak, so these are all mass units, and we got a peak at 1 mass unit, that could be a hydrogen nucleus, a proton. I'll use those two terms interchangeably. I'll call hydrogen when it's an atom. Sometimes I'll just call it a proton, especially if it's charged. If the electron's removed from a hydrogen atom, then all you have is a proton, just a proton flying through space. Mass 1, and the electrons don't add anything to the mass in general. They're a tiny fraction, about 1/2000th of a proton. So it's a tiny fraction. In this case, just a proton. Here, I'm adding a peak at 2. That, now masses aren't unique, so you don't know exactly what that is, but if you know what you shot into the spectrometer, you'd have a pretty good idea. So that could be a hydrogen molecule at mass 2, or a H2, a hydrogen of mass 2, an isotope of hydrogen. So we have these things called isotopes. They're the same element, same number of protons, but they have a different number of neutrons, so they have a different mass. So heavy hydrogen, it's twice the mass of by adding a neutron to the nucleus. Isotopes have very, very similar properties. In this case, the properties can be kind of dramatic because the mass doubles when you go to an isotope. In general, on a bigger nucleus, if you add just one more neutron, there's not such a big change in mass. So here at mass 3, you could have a helium nucleus that has relative mass 3, or a hydrogen molecule with one of the atoms of deuterium. Deuterium is the name of the hydrogen isotope with mass 2, and hydrogen. So hydrogen mass 1, hydrogen mass 2 together would give you a mass 3. And you can go on. Here we have mass 12. At mass 12, you might have a carbon nucleus. Here's mass 13, a carbon 13 nucleus. And in a natural sample, that ratio, it's not correct here, would be 100 to 1. Because there's about 100 carbon 13s per carbon 12 in nature. We can keep going. Here's a peak at 16. That could be an oxygen atom. Here's a peak at 18. That could be water with 2 oxygen 16s. Or it could be an oxygen 18 atom. And we'll keep going. So here at 32, we just saw that relative mass, an oxygen molecule, both of them 16. But you could also have oxygen 16 and oxygen 18. So those are isotopes. This oxygen is a heavier isotope. It has 2 extra neutrons in the nucleus, but it's still oxygen. So this oxygen molecule does pretty much everything any other oxygen molecule does. It's slightly heavier because it has, and you can detect that in a mass spectrometer. You could have 2 O18s in the molecule, and then you would have an O18 here at mass 36. Oops. Let's look at the rest of them. Here's carbon dioxide with carbon 12s and oxygen 16s at mass 44. And here's carbon 13 carbon dioxide. And naturally in the atmosphere, that would be the ratio of 1 in 100 again, because that's about the ratio of carbon 13s to carbon 14s. Carbon 13 is not a radioactive nucleus. So it stays at this ratio of 1 to 100 in natural carbon, whether it's been dead, not exchanging with the universe, or has been exchanging with the universe. That ratio stays the same. But over the course of generations, millennia, the ratio of carbon 12 to carbon 13, I keep touching the board, I'm sorry, carbon 12 to carbon 13 in the atmosphere has changed because of a lot of factors. How much carbon the ocean absorbs. The carbon 13 O2 is slightly heavier, so it's likely to be more interacting with the surface, more of it near the surface of the Earth than in the upper atmosphere. So the mixture of this to this has changed over the years, the millennia, the millions and millions of years. But we can kind of detect what it was millions and millions of years ago, the ratio, by going and taking a sample of some carbon substance from millions of years ago, like say oil, coal, something that came from ancient carbon dioxide or was present in ancient times. It would have a slightly different ratio. And using that information, the ratio is different today. We can actually detect, there's this whole issue of global warming, and people say, well, sure, there's more carbon dioxide in the atmosphere. Is it coming from human? Is it coming from burning fossil fuels? Yes, it is, because we can see the carbon concentration, the relative concentration of those 2 isotopes changing in our atmosphere and becoming more like ancient carbon. So we keep adding this ancient mixture to the air by burning it, and we can detect that. So don't let anybody tell you this is just a natural cycle that is coming from human activity. So let's look at a mass spectrum. So here we're going to take an equimolar mixture of, now I use the term equimolar here by mistake. I'm doing this slightly different order. Same number of particles, equal number of oxygen 16 and oxygen 18 particles. And I'm going to put them in a flask. Oxygen 16 particles, oxygen 18 particles as atoms. And I'm going to let them react to form oxygen molecules. Completely react. That would happen very fast. And I'm going to take that sample, once it's all oxygen molecules, and inject it into my mass spectrometer. And I wonder if you can tell me what the mass spectrum would look like, what the ratio of those peaks would be at the various masses that are shown here. So I'll start a chem quiz. Think about that in your breakout rooms. Chat about it together. I'm going to switch. This should be captured now in your app, your iClicker app. So I'll go to this page, which will give you some more information that might be helpful. did I? Oh, I forgot they can keep talking. Hi guys, I'm back. Had a great discussion in a Zoom room. My Zoom room, funny, 3 or 4 out of 5 of them are just like in Fremont and very close by, but randomly assigned to the same Zoom room. They could probably be visiting at each other's house right now almost. And of course, close enough to come to campus. You can come to campus and sit here in the live studio if you'd like. We have a procedure for doing that. You email Ben, one of the student instructors. There was a long procedure listed in the email that went out inviting you. Those rules apply to students, matriculated students. So many of you haven't actually been, you've been accepted to Cal, but you haven't been here yet. And many of you are just from other institutions or in high school. So you guys are welcome to come. If you're coming to Berkeley in the fall, try to meet all those requirements. Get the Berkeley app and do the screening. If you're not, we can't require you to do those things, but we still want you to come. So just have a vaccination card that says you're vaccinated. You can come into the building. We're allowed to accept you into the building. Wear a mask if that is appropriate. In this room, the students are wearing masks. I'm not, so I can talk to you, but please come visit if you feel like that. And just sign up with Ben, pick a day, and come and see us. So let's see what you're thinking about that one. So many of you have chosen B, and I like that because I agree. Oops. I agree with the B's. Sorry, I'm fighting with the iClicker. So why is B correct? Well, if you take the particles, oxygen 16s, they look out and they see some number of oxygen 16s. They also see a bunch of oxygen 18s out there. So they can collide with a 16 or an 18. So they can form a peak at 32 mass or 34 mass. Oxygen 18s are also colliding, and they can collide with an oxygen 18, and that would make a 36 mass, but the oxygen 18s can also knock into oxygen 16s. So this combination is more likely. You get twice as many of those kind of collisions as you do those kind of collisions, and that leads to twice as many of the particles that have mass 34, an oxygen 16 and an oxygen 18. Great. I didn't think that this showed up here, but it does. So let's do this. Let's try it again. This is similar to what we did. What mass in grams of methane is required to completely react with 4 grams of oxygen as shown? So 4 grams of oxygen and how many grams of methane, what mass of methane is required to react here? We just went through this in lots of detail with the sulfur and oxygen. I think we're going to skip over this one because we did go in a lot of detail with sulfur and oxygen. This is the same. I'll just go through the procedure. The relative masses you can calculate. Carbon has relative mass 12, and 4 hydrogens has each with relative mass 1, would give you methane relative mass 16. Oxygen we've already seen many times, relative mass 32. So their mass ratio is 1 to 2. So you could do 16 to 32, but 1 to 2 still works. So 1 gram of methane has the same number of particles as 2 grams of oxygen molecules. Makes the calculation pretty easy again. You just have to be careful this time. A mass of 1 gram of methane, I've written the word mass here because this could be any mass unit. It could be kilograms or pounds. So one mass unit of methane has the same number of particles as 2 mass units, 2 grams of oxygen. So if you have 4 grams of oxygen, 2 grams of methane would have the same number of particles. That mass ratio, 2 to 1 still. And in this case, though, a particle of methane reacts with 2 particles of oxygen. So every methane that reacts requires that it has 2 particles of oxygen to react with. So if you have 4 grams, you have the same number of particles like this. Every gram of this reacts with twice as many particles. So every gram here will react with 4 grams there, twice as many particles. So you can write that out. 1 gram reacts with 4 grams because now there's twice as many particles here as there are here. And that's what you need, twice as many particles here as you have here. So the complete reaction requires just a gram of methane to react with your 4 grams of oxygen. Okay? Fantastic. Oh, I just noticed it doesn't matter what these masses are. 32 grams has the same mass as 16 grams. So if you had 32 grams, you need half as many. You need 8 grams of methane. Doesn't matter what the mass units are. That's the lesson here. Okay, so we'll continue on here. Here's a combustion mass spectrum. So let's do this one. So the combustion of a hydrocarbon with oxygen yields the products with the mass spectra shown. So you do a combustion, you burn one of these in oxygen, and you get that mass spectrum. The question is that enough information? Can you tell which hydrocarbon that is that you burned? So think about that for a second, and we'll chat and take a vote. Okay. We're back. Great discussion in the discussion rooms. Let's see what you're thinking. Many of you are thinking it's acetylene. So it's in kind of 2/3 and 1/3 for the other two, about 25% ish, 30% ish for A and B, 60% for C. So that's what that looks like. Let's see what my thinking. Let me tell you what my thinking is. So the mass spectra had peaks at 18 and 44, and I think most of you realize that's water, relative mass 18, and carbon dioxide. And I told you yesterday, if you take nothing else home from Chem 1, take home the fact when you burn a hydrocarbon in oxygen, you get carbon dioxide in water. In general, I'm not going to just tell you that on an exam, or you just have to, I assume you know it. So you get carbon dioxide in water. The question is, what ratio do you get? You could have done this a lot of ways. You could have just written all the various combinations. If you burn carbon dioxide in water, all the hydrogens in the water had to come from the hydrogens on the hydrocarbon, and all the carbons in the carbon dioxide had to come from the carbon in the hydrocarbon. So oxygen does not matter. Of course, these oxygens are coming from the oxygen, but the hydrocarbon parts are the one you're interested in. So if you burn methane, you would get 2 water molecules for every carbon dioxide, because the ratio has to be 4 hydrogens for every carbon dioxide. So 2 molecules, or twice the relative mass showing up in your mass spectrum. Mass spectrum counts all the particles, and 1 mass, relative mass of, or relatively half the mass of carbon dioxide particles. So you can just do that with all the various combinations here. You could just work backwards from the spectrum. You could say here the masses are equal, so there's a carbon atom. For every carbon atom, there are 2 hydrogen atoms, because there's a water and a carbon dioxide. So equal masses means 1 carbon to 2 hydrogens. And you could say, well, there's 1 to 2. That's the ethylene. And of course, for the acetylene, the ratio is 1 to 1. And that gives you a ratio of a 2 carbon dioxide. So you need 2 carbons for every 2 hydrogens, 1 to 1 ratio. And that's what you see there. So fantastic. Nice job, guys. I agree with the acetylenes. So this brings up an interesting point, that the ratio of the atoms could be actually different things. The hydrocarbon that gives you that first mass spectrum that we showed there, here, that gives you that 2 to 1, that hydrocarbon could have been any of these that have the same ratio of carbon to hydrogen in them. Could have been any number of molecules, as long as it could have been any molecule that had 2 to 1 ratio. But these are the various just straight carbon hydrogen molecules it could have been. Here, if it's ethylene, it also could have been CH2, C2H4, or C3H6. And here, acetylene gives you CH, C2H2, and C3H3, 1 to 1 ratios of carbon to hydrogen particles. So there's each of these compounds have the ratio of particles that look like this, and the mass spectrum only gave you the ratio of particles. So that means we call this simplest ratio of particles, the simplest formula you could write. So you can divide that one by 2, and you get 1 to 4, and divide that one by 3, and you get 1 to 4. The simplest ratio, the lowest common ratio of the particles, the atoms in a molecule, is called the empirical formula. And it's called empirical because empirical means what you would get if you did an experiment. It's the experimental result. And in the experimental result, like we just did, all you could get was the ratio. You got the empirical ratio of the two. There isn't a way to determine with just that data what you had. You could very carefully measure masses to start and finish and figure out what you had, but just that ratio gives you just the empirical formula. These are actual molecular formulas. They are the actual molecules, the ratio in the molecules themselves. Difference between those two things, and you might see that in your homework. Okay? These were the, why did I highlight those? Because those were the ones in the Chem quiz. Okay, so let's talk about relative mass now, and let's add one more concept. And you knew this was coming. You guys have all been trying to use this whole mole idea the whole time. If you go back to the hardware store and you want to know how many exactly bolts and nuts and washers you're getting in your metric ton of bolts and your metric half ton of washers, there is a way to count them. You can count them if you know the exact mass of an individual one. That helps. That's easy to do with bolts and nuts and washers. Not so easy to do with atoms and molecules, although that mass spectra will give you, that mass spectrometer will give you exact masses down to electrons, down to fractions of proton masses. So it's exquisitely sensitive to mass. It's almost mind-boggling how exact a mass you can get from a mass spectrometer. In a sample at the hardware store, they still don't like to sell them by the each. They don't want to give you one bolt or picking them out one at a time. But if you're going to the hardware store, they'll sell them to you in boxes. They'll sell you a box of 100 bolts and a box of 100 washers and a box of 100 nuts. And that makes it easy too, because then the ratio is 1-to-1 in boxes, because there's 100 in each box. So you could say, give me 10 boxes of bolts, 10 boxes of nuts, and 10 boxes of washers if you need equal ratios, or 10 boxes of bolts, but give me 30 boxes of washers because 30 boxes of washers because I need 3 washers in my example for what I'm doing for construction, and give me 40 boxes of bolts because I need 4 bolts or 4 nuts on each bolt, or you get the idea. If they come in boxes, you can use boxes just like you could use grams or pounds or the mass unit. But the advantage of the box is it tells you the number of particles exactly, which is the relative mass. Unless you know the mass of one of them, you don't know how many are there. And that's what we do in chemistry, because the mass of one particle is, vanishingly small, and we can't weigh it out on our scale in the laboratory. It's too small a mass. So rather than that, we do say, give me carbon in boxes, and put the same number of atoms in each box. So if I buy carbon and hydrogen and oxygen molecules and hydrogen atoms, always put 100 in a box, and then I can just buy by the box. I'll know the relative masses of those boxes. Since there's the same number of particles in each, the relative masses are the relative masses on the periodic table. The box is sometimes easier to think about. So what does that mean? We do the same thing. We take boxes of them. We call the boxes moles. And rather than 100 is convenient with macroscopic things. For microscopic things, the number has to be ginormous to get to a couple grams that you could weigh out. So if you get to grams of particles, it's a tremendous number of particles. So macroscopic bulk matter is made of our atoms and molecules, and we are going to take as our reference mass 12 grams of carbon-12 particles. So we're going to say, put in each box the same number of particles that 12 grams of carbon-12 has. I don't know how many that is, but if you did 12 grams of carbon-12 and you put the same number of particles in every box, then you would take your box of oxygen atoms would have a mass of 16 grams, and your mass of carbon dioxide, your box of carbon dioxide atoms would have a mass of 44 grams. So you can still use the masses or the boxes. The boxes with the equal number of particles have the relative masses. We're going to call the boxes moles, and the reference, we refer them all to figure out how many particles to put in. We refer them all to 12 grams of carbon-12. So a 12-gram box of carbon-12, or I'll just start saying mole now. 12 moles of carbon-12 has a certain number of particles. The same number of particles would be in a 16-gram mass of oxygen or a 44-gram mass of carbon dioxide. The actual number, we give the symbol N0. We call it Avogadro's number. He was some ancient chemist who figured it out or came up with the first approximation of this number, and it's ginormously large, 10 to the 23rd particles. So 10 with 23 zeros, that's a spectacularly large number. So it takes this many particles, 10 to the 23rd particles, to get yourself up to 12 grams of carbon dioxide. And if you took that many particles, did I just say carbon dioxide? I might have. 10 to the 23rd particles of carbon get you up to a mass of 12. 10 to the 23rd particles of carbon dioxide would get you up to a mass of 44, because each individual carbon dioxide is heavier, and we know the relative masses. Okay, so that's a relatively straightforward concept, but in some presentations in chemistry books, it just ends up confusing people. It's called the mole concept, but because you call it a mole concept, that somehow makes it something that you have to learn from scratch. You don't have to learn it from scratch. It's just the relative masses, and you put stuff in boxes or moles, so it's easy to make sure you have the same number. That's that. This historical stuff, Avogadro's number. In general, I will not ask you to know anything historical or even the names of equations or the names of people. None of that shows up on any exam you'll ever see from me. Okay. I think the historical nature of chemistry is so fun to read about. Please do. There's some of that in the text references. I also try to give you text references that don't have any historical stuff in them, because it's just a distraction. You don't need to know any of that. I just want you to know the concepts and the science. But by all means, if it's a great read, pick up a book on the history of chemistry. It's just really fun to read how these things were actually done and the circuitous paths. But in not ancient times, but in just post-medieval times, people were fooling around with chemicals, and even back then, with no accurate, no mass spectrometers, none of that stuff. They were getting to estimate these just by reasoning it, just like we reasoned it, just like the hardware store reasoning. So we're going to define this thing called the molar mass. What is the mass of one mole? And we've just been saying that. The mass of this many carbon dioxides is 44. The molar mass of carbon dioxide is 44. How much does one box weigh, one mole? All right. Okay, so now let's try it. How are we doing? 2 moles of an oxide of hydrogen, so some oxide of hydrogen, one of these, has just hydrogen and oxygen in it. Release a mole of oxygen and leave behind pure water. With that information, this ratio of boxes of particles and numbers of particles, so no mass this time, which is the oxide if you know this information? So think about that for a minute. I will start this. And I forgot to open the demos. I'm not going to join a Zoom room this time. I'm going to mess around and try to get the demo loaded up. So think about that for a minute. We'll take a vote. Okay, coming back. Sorry, I covered this, but some of it it should be captured in your quiz app. So let's watch the reaction as long as it's here. I think the reaction has has the name of the compound on it. Oh, I'll look at what you guys are thinking. Many of you, 91%, thinking H2O2. That's called hydrogen peroxide. So let's watch Lonnie do it in real time. So Lonnie is going to take this hydrogen peroxide, and notice it's sitting there stable on the counter. So just like the hydrogen and oxygen in a balloon, this manganese oxide is a catalyst that catalyzes the reaction of that decomposing to water and oxygen. And there it goes. So that gas is a mixture. The reason it's kind of opaque colored there is it's a combination of water and so if I go back to the PowerPoint, it's a combination of water and oxygen coming off there. So steam and oxygen gas. So you could do it, kind of the ratio of particles. So kind of the best way is to say, well, if you reacted these with oxygen, what would the each itself give you? So if you reacted just that, you would get 2 moles of oxygen or water and 1 mole of oxygen. And that's about the right ratio. So it releases one, it's the 2-to-1 molar ratio. And I didn't tell you how many particles of water, I just said there was some. So the 2 there doesn't matter, but that makes sense in doing that. So you could work kind of backwards and do that with each one of these to just balance out the particles. Okay, fantastic. I think that's what many of you did. Here's the reaction we saw last time. Hydrogen, oxygen, and water, all in balloons. That would be tricky to make it happen in balloons. We know these things explode concussively. It's interesting when we did this, the most common answer when I asked you for which releases the most energy was the oxygen gas. And we know why that, well, I think I know why that is. If you watch the movies, there's always, you'll see these tanks of oxygen, and it's setting the scene, the tension, because a cigarette or something will come in and that oxygen will just go up like crazy. That doesn't happen. Oxygen by itself does not explode. It has to react with something. You burn things in oxygen, but you need some fuel. So there's the famous, anybody a Deadpool fan? One of my favorite movies. Watch it if you haven't. So the origin story for Deadpool is he's in a hyperbaric chamber and they start filling it with oxygen. And to get himself out, he, what did he do? I think he smuggled a match in. He smuggled in a matchstick into the hyperbaric chamber. So oxygen is pouring in, and he says, man, if I can get this matchstick lit, the whole thing's going to blow up. He is wrong. The match will burn quite brightly, probably, but the whole thing isn't going to explode. If all the fuel you have is that matchstick, the thing is not going to blow up. So movies do it wrong all the time, and that's where you get these misconceptions. And I know you have misconceptions. Sometimes I know where they come from, but we try to dispel them as much as we can in this class. They actually create a barrier to you your learning, because you have this conception of what happens. You have to throw it away and start from scratch to see what's happening. I wish they would just ask me as a consultant. The consultants probably make lots of money to get the science right for them. So here we now can write this out in many, many ways. So we can start using this number of molecules or mole technology terminology. We already have been using the particle and mass terminology. 2 particles of hydrogen molecules react with 1 particle of oxygen to make 2 particles. So if they react by particle, they would react by millions of particles. So 2 million would react with 1 million. Or 2 Avogadro's numbers, 2 times 10 to the 23rd would react with 1 times 10 to the 23rd to give you 2 times 10 to the 23rd molecules of oxygen. Avogadro's number is at 6.02 times 10 to the 23rd. I'm just going to say 10 to the 23rd or mole or something. Once you're at 10 to the 23rd, whether you have 6 times it or not, it's 10 to the 23rd. So 2 moles would react with 1 mole to give you 1 mole. So you can substitute 1 for 1 particles to moles, of course, because that's what a mole is, just a number of particles. In this case, liters of gas would be 2 to 1 to 2. And we'll learn why that is. But basically, gas takes up space. The more particles, the more space. So twice as many particles gives you twice as much volume of gas. And mass ratios we can get right from the number of particles, but we can also get it just from the formulas. We know the mass ratios, a relative mass, 32 to 2 in this case, and 18. So to get the exact masses, you need 2 relative masses of hydrogen because you need twice as many particles, 1 relative mass of oxygen, and 2 relative masses of water is your result. And the mass on this side better add up to the mass on this side. So 4 grams and 32 grams is 36 grams, and you get 36 grams of water. You don't lose any particles. No particles disappear in this course. So if all the particles go from this side to this side, all the mass has to go from this side to this side. Mass is going to be conserved. In general, if you're in engineering classes, everything you do, every problem you look at, you conserve mass and you conserve energy, and you work out everything from those 2 fundamental concepts. And we'll do that, a lot of that too. We'll conserve energy, but mass is always conserved too, and we can fall back on that at any time to determine what's going on. So mass is conserved. The number of particles not conserved. So there's 3 moles of particles on this side. There's only 2 moles of particles on this side, 2 molecules. So particles aren't conserved. Neither is volume. 3 liters on this side, 2 liters on that side. Number of moles not conserved. 3 moles total on this side, 2 on that side. If you took your 2 boxes of nuts and attached them both to the same bolt, you would have just 2 bolts. The bolts kind of say, well, there's 2 nuts attached here, but the total number of units, bolt, nut, is just 2. Okay, let's work it out. Let's do a little calculation here. We'll end with this. I'll go through this quickly. You have the slides you can download. I just wanted to give you a feeling of dimensional analysis. Dimensional analysis is a powerful tool. You can change 1 dimension, a mile, that's a dimension, a length dimension, to another length dimension, feet. If you know how many feet are in a mile, you can divide both sides by 5280, and that ratio is 1. Divide both sides by that. So that means you can multiply this quantity by anything. You don't change its fundamental value. You're multiplying by 1. All you do is change its dimension. You change its unit. So same amount of stuff, but same length, just expressed in a different unit. So I can convert between miles and feet if I wanted to, by multiplying the number of miles by this inverted. I can also, that's important, I can invert it and it's still 1. So I can go miles to feet or feet to miles. We'll do that here with particles. 1 mole of particles is 6.02 times 10 to the 23rd particles. So I can convert between particles and moles, change their unit by multiplying by this quantity. And I can do that multiplication because the units will cancel when I do the multiplication. So let's look at that multiplication. Here it is. Again, the conversion factor from miles to feet. So how many feet in about a quarter of a mile? Well, take your quarter of a mile, multiply it by the appropriate conversion. So I can invert these, go up and the feet over the miles either way, but you multiply so that the units cancel. This is in the numerator, that's in the denominator. And if you do that, that product, 0.23 times 5,200, 1,200 feet is the number of feet in about a quarter of a mile. So straightforward, easy to use, but super powerful. You'll end up converting from one unit to another frequently in all your science classes. So physics, chemistry, and you'll use this repeatedly along with conserving mass and energy. So let's say you win a mole of dollars. Let's look at how big that mole of dollars is. Is it more than Jeff Bezos has? Is he the richest guy these days? It goes back and forth. But if you win a mole of dollars in a lottery, but you could spend $1 billion a second, that's clicking really fast on Amazon or buying the big ticket items. Isn't it Amazon days right now? I think it's Amazon Day was, I think it's the 21st through the 25th. I don't know why I'm advertising for Amazon, but deal days at Amazon. If you go and you spend $1 billion a second by clicking like a mad person on Amazon.com, how long in years would you be clicking, spending $1 billion a second? How long? And would the Prime delivery get it all there the next day? I don't know. So let's take our mole of dollars, 10 to the 23rd dollars. And we want to talk about spending dollars per second. So $1 billion, 10 to the 9th is $1 billion per second is how fast we have to spend it. And we have to spend all of these. So let's just, technical difficulties. Stand by. How long would it take? So let's just do conversion factors. Convert from dollars per second to dollars per year. Let's do that. So here's dollars per second, $1 billion per second. I think you know, maybe not how many seconds there are in a year, but you know how many seconds in a minute, 60 seconds per minute, right? That conversion factor with the seconds on the top, so they cancel with the seconds on the bottom. Go from minutes to hours, because you know there's 60 minutes in an hour. That gets you an hour. We're trying to get to year, so we got to keep going. There's 24 hours in a day. Now we're up to days. So we're in dollars per day by this point. Let's go to dollars per year with our 365 days a year and start canceling the units. The seconds cancel, the minutes cancel, the hours cancel, and the days cancel. And it gives us dollars per year if we multiply through now all just the numerical values and multiplying through the numerical values, 10 to the 16th years to spend a mole of dollars at $1 billion a second. So 10 to the 16th years. Does anybody know how old the universe is? Billions of years. You know, 5 billion-ish years, the universe. So something like that's billions of years is the universe. Something like 10,000, we need 6 more, 1 million times ish or more the age of the universe to spend a mole of dollars at $1 billion a second. Okay, wonderful. We'll see you all tomorrow. Have a good day.